Good afternoon, everybody. My name is John Mellor-Crummey. I'm a professor at Rice University. This is my student, Yuning Jia. We're part of the HPCToolkit project at Rice. So HPCToolkit is an HPSF project. We've been building performance tools for use on DOE applications for around 20 years. And so over the last several years, the focus has shifted to the exascale platforms, which have a range of GPUs, so discrete GPUs from AMD, from Intel, and the MI300 APU, which has both CPU and GPU cores, as well as NVIDIA systems are of interest. And so in this talk, I'm going to tell you a little bit about measuring performance on GPUs, tell you a little bit about our HPCToolkit performance tools and some work that we've been doing recently on instruction level performance analysis of GPU kernels with HPCToolkit. And then Yuning is going to tell you about some instruction level root cause analysis that he's been doing in the last 2 months or so. So first, for just a little bit of level setting, when people are measuring performance on GPU accelerated applications, they're using profiling, which measures the time that's spent in each of an application's operations, and so that might be kernel launches and data copies typically. You also do tracing, where you're measuring and reporting the time in individual GPU operations, and so often you use these traces to visualize things over time to see how the execution is progressing. Another technique is to measure hardware performance counters, and so you can measure instructions of various kinds, scalar instructions, vector instructions, memory accesses, the number of wavefronts there are in the GPU, cache misses, stalls, things like that. So you can get a lot of information about what's going on in the GPU, and there's hundreds of performance counters. So for these kinds of measurement approaches with profiling and tracing, they're good for assessing the utilization and the load balance or load imbalance across the GPU. You get to see how much you're using it, and you get to see how you're using it over time. But what if you find you're spending too much time in your kernels? Then the question is, well, what's going on? So if you use hardware counters, you can assess what the kernel characteristics are. You might find that there's a lot of data movement that's happening between, say, the compute units and main memory. Or you might find that there's a lot of divergent branches, which means that your threads are doing different things. And so you can tell whether a kernel is efficient or not, and if not, why. But it also tells you nothing about where the problems are. And so this is particularly a problem with complex applications. And so our poster child for the complex application is a code called Mercury from Lawrence Livermore. It's a Monte Carlo code, and what they did is they found it difficult to do sort of a straightforward parallelization of the code. So in effect, what they did is they took the entire Monte Carlo code and they put it inside a kernel. So there's about 100,000 lines of code and about 2,000 procedures, and that's what happens inside the kernel. And there's only one or a handful of kernels in the entire application. And so if you tell them the kernel is too slow, they'll say, duh. And of course it's slow, but we have no idea why. And if you tell them, well, there's too many divergent branches, they would say, well, we have 100,000 lines of code. Which branches are those, right? And so it's hard to understand how the performance costs relate to the code and how to identify the root causes of these inefficiencies. You know things are bad, but you don't know where, and you don't know what to do about it. So the approach that helps with this is something called PC sampling. And so as you all probably know, GPUs employ a large set of processing elements for massive parallelism. And so on NVIDIA GPUs, these are called streaming multiprocessors. And so for a level set on the Blackwell GPUs, there's 160 of these streaming multiprocessors. And so you can think of them as being kind of like cores in a CPU. These are like the basic units of computation engine inside an NVIDIA GPU. On AMD GPUs, they're somewhat similar. They're called compute units. There's 228 of these in an MI300. On the Intel GPUs, they call these ZE cores, and there's 128 of those in the Data Center Max GPUs, the Ponte Vecchio GPUs that are in Aurora. And so with PC sampling, what you're doing is you're measuring kernels at the instruction level as they execute. And the way that this works is you're periodically sampling an instruction on each streaming multiprocessor or compute unit or ZE core. So I'll just say streaming multiprocessor from now on, because that's the terminology that most people know from working with NVIDIA GPUs. And so what is going on is you're interrupting the GPU and sampling an instruction, and then recording the GPU instruction addresses as the program executes. And then after the program execution is done, then we map the instructions back to the source code in postmortem analysis. And that tells us like where we're spending our time. So a brief history of this. So back in 2013, myself and my students engaged in NVIDIA, and we told them that their hardware performance counters were kind of suxometers, that it told you that there was a problem, but you had no idea where it was. And so we talked to David Goodwin and asked about some instruction level performance monitoring, and he said he thought that they could do that. And so and soon thereafter, they released the Maxwell GPU that had support for that. And then they've added some new lighter weight software support for that in 2021. Then as part of the exascale computing project, my group engaged with AMD and with Intel, and they also added support for PC sampling for this instruction-based performance measurement inside their GPUs. So NVIDIA has their CupT performance tools interface. Intel has their metric API for collecting PC samples, and AMD has their Rock Profiler SDK. And so there's two important things to know. One is what you would like not to do is to have to serialize kernels in order to measure them. And with the old NVIDIA infrastructure, you had to serialize kernels to know where a kernel was launched from in order to be able to attribute your performance information. In their new lightweight PC sampling, you don't have to serialize the kernels, but you can't tell where they're being launched from. And so this means that you know that somebody called matrix multiply, but you don't know who launched, like what thread launched it or where or whatnot. And so there's some issues with that. With Intel's metrics API, they don't provide any way of correlating these PC samples back to the launch context either. And so in our tool, Uning built something that serializes kernels as sort of a stopgap solution. The best case was we were able to talk AMD into putting support into their Rock Profiler SDK, where they will actually give us a correlation ID for every PC sample, so we can tell which kernel launch it was associated with, and so we know sort of like what thread and what instance of a kernel launch the performance information came from. So in the MI200 series of GPUs, and so this is for the Frontier system, we missed the hardware freeze window, and so the PC sampling couldn't go into the MI250Xs. And so instead what they did is they built a software approach where you'd periodically freeze the GPU, extract the program counters from each compute unit, attribute each PC to its kernel with a correlation ID, and then we would map these machine instruction addresses back as long as you compiled your programs with -G in addition to whatever optimization flags you had. And so how does this help? Well, it identifies where your kernels are spending their time. So with PC sampling on NVIDIA's GPUs, on their streaming multiprocessors, what happens is every P cycles, where P is your period, there's 4 warp schedulers on each of the streaming multiprocessors. And what happens is the hardware is going to select one of the instructions that is from one of the warp schedulers. And so the instruction over here in the dark blue, the instruction might not be ready to execute. Maybe it's waiting for a dependence to be satisfied, maybe it's waiting for a value from memory, and so the instruction might be stalled. And then the next time we take a sample, another period later, we sample another stalled instruction. And then the same is true the next time. And then the fourth time we sample an instruction, this instruction is ready to run, but it actually wasn't launched because it launched something else. And so that's okay. Like I have an instruction that's ready to go, that was sampled and I can tell it's ready to go, but another one was chosen. And then finally we might sample an instruction that is actually being launched. And so what this does is it gives us a picture of what's going on inside the streaming multiprocessor to tell us there's a bunch of seething instructions that are trying to be launched on the compute engine, and sometimes they're not ready, but then eventually they will get initiated when all of their dependencies are satisfied. So when you have this sort of hardware support, then NVIDIA's GPUs, now AMD's and Intel's GPUs are all collecting information about stall reasons. And so you can tell that you're stalled where you're waiting for a value from memory, you're waiting for a branch target to be computed. If you have like an if then else, you may need to wait until like the branch is computed if I have to go to the else branch. We may stall for an instruction fetch where you decide that you're taking a branch to somewhere unexpected, and then you have to wait while the instruction is fetched from the location that you just branched to. There's synchronization stalls where you're waiting for other threads to arrive. You're waiting for memory. You can't issue in a memory instruction because the memory issue queue is already full. The pipeline is busy, so I want to execute a vector instruction, but there's no slots left in the vector pipeline, so I have to wait. Or my instruction is not selected, or it's sleeping. And so these are all things that we can find out for an individual instruction. If the instruction is not ready to go, we can understand why. So GPUs use a high degree of multi-threading to hide stalls. And so like on the AMD GPUs, there's 32 active wavefronts inside a compute unit. And at any point in time, it's going to select a couple of these instructions to execute. And the idea is that if my instruction stalls, hopefully one of the other instructions that are on deck can be issued. And so if my instruction stalls, so let's say that I'm a vector instruction and I stall, but there's some other vector instruction that's ready to go, and so there's an instruction ready to issue in the vector pipeline, then it doesn't matter that my instruction that was sampled stalled. What matters is we're making forward progress here and somebody gets to go and the execution unit is not being starved. And so that's what matters. So inside the HPCToolkit performance tools, you launch your application with HPCToolkit, and we collect profiles which include this instruction level information. We also collect traces, and then we analyze your binaries to recover information about the mappings between the machine instructions and the line map, and then we put it all together and we have a viewer for it. And so we can visualize traces at large. We can collect and visualize traces at large scale. There's graphical views. I'm not going to talk about that, so we're going to focus on the profiling here. And so we unwind the call stack to attribute costs in context. And so the thing that's important here is that we're unwinding the call stack to capture the context for GPU kernel launches. So here, let's say I launched a kernel at a particular point, and I understand that I'm launching a kernel inside C when called from B, when called from A, when called from main. And then over time, there's all sorts of contexts that are being sampled, and so one of these contexts is a kernel launch, and so then we're collecting the PC samples and we'll hook them into this calling context tree underneath the kernel launch. So what does this give us? Well, what we're able to do is we're able to map this back to the source code using the information that we scrape out of the binaries. And so this is a case for a code called Pele C. that does combustion simulation. And what we found was that there was a lot of time that was mapped back to a loop. But it turns out that with our binary analysis, we figure out whether the instructions are inside or outside the loop. And it turned out this instruction was actually outside the loop. And so it mapped back to the line of the loop, but outside the loop. And it turned out that what it was is that because of the way that the lambda capture was done, the lambda capture was capturing the pointer to a structure. And so then when the values were dereferenced, there was like a unified memory miss. And so it took a long time. There was a long memory delay there. And so it turned out that when the developers got this information from us, they changed their lambda capture so that it was passing scalars, and this saved 4% over the entire program just by fixing this one line in their application. So in the AMD GPUs, we can measure a lot of information with the PC sample. So we can measure where the sample was collected, what chiplet it was on, what compute unit, what SIMD unit, how many wavefront slots are full or not, how many threads are active, what instruction was sampled, what its machine code address is, and what kind of instruction it is, and whether the instruction stalled, and if so, why. And also, we get information about the pipelines. Are the pipelines active? There's matrix pipeline, vector pipeline, scalar pipeline, flat memory accesses, the local data store accesses, texture memory, and also branches and this messaging facility. And so for each pipeline, in every time we take a sample, we know whether an issue was attempted, whether the issue was successful, did the issue stall because of lack of resources, or was the pipeline idle? There's a wealth of information we get from these samples. So the question is, what are we going to do about it? Well, until last week, what we did is we gave you 100 columns, okay? 100 columns worth of numbers saying this is how many pipeline stalls we measured and how many instruction issues we measured, but that's not that good. So what we decided to do was to follow the lead of Intel. They had done this top-down model for CPUs. And so the idea is that for instructions that are retiring, so this is on a CPU, if the instructions are issued and they're retired, that means that they're usable. And so this is the good stuff. Bad speculation means that I predicted that I was going to go around another iteration of the loop, and I started executing instructions from the next iteration, and it turned out I was supposed to break out of the loop. And so bad speculation is like useless execution. Or you're like waiting to fetch instructions, or you're trying to execute instructions and maybe you're waiting for instruction dependencies or you're waiting for memory. And so we tried to, so this basically is like a tree-based structure, and so we built this tree-based structure for top-down analysis on the CPUs, but then we took this idea and we said, well, let's apply it to look at all the information for the GPUs. So we have here is this tree-based structure that's sort of the same idea, where we get to see whether there's an exposed stall, whether it's a stall in the back end or a stall in the front end waiting for compute or memory, or in the front end waiting for instruction fetch, and then for instruction issues, we can tell whether they're communication instructions, control flow instructions, memory instructions, or scalar or vector compute instructions. And then the tree is displayed as this donut graph, which you may or may not have seen before, but the idea is that the root is here, and then its children are circled around it, and then the children at the next level follow around that. And so this basically tells you all of the information here, and if you had this live, you would hover over it, and you would get to see what the color corresponds to in this tree. And so here's the last slide I wanted to show about that. So this is looking at the same code. So this is a Monte Carlo code called Quicksilver, which is derived from the Mercury code. And on the left is the donut graph that shows on an A100, and the same function inside a kernel is shown on the right. And you can see that there are remarkably different shapes in these graphs, and over here, there's about 50% issues, And over here, the number of issues is pretty small. It's just like 16%. And so why these things are vastly different, we haven't had a chance to dig into that yet. Okay, so that's what we've been doing for the instruction level analysis. And so we're going to work on some visualization of the compute unit resources and the pipelines next. And so next, Yuning is going to give you a brief rundown on what he's been doing on instruction level root cause diagnosis.
Thanks, Joe. So thanks to the years of contribution from the HPCToolkit group to support the PC sampling in for all the all three vendors' machines, NVIDIA, AMD, and GPU, and Intel. So now I think it's a great timing to go further to do deeper instruction analysis on how to find the issues and how to optimize the code in an efficient way. So basically, the PC sampling can tell us the per instruction style distribution across the kernel and tell us which kind of instruction is styled and for what kind of reason. But here there are two issues still there in the community. The first one is so currently all the profilers from vendors they can tell us which kind of styles are accumulated in which line of code in a specific file. But these kind of things are all about symptoms. The style will actually be caused by something previously. Maybe it is a memory style, and it is because you are waiting for loading some data from HBM. So actually the real reason behind this is on some previous line of code. Maybe there are some global load at a line, maybe 38 in one specific file. And this is actually where we should go deeper and to fix. And if we want to remove the bottleneck in the line maybe 42, we actually need to fix the line maybe 38 to actually eliminate all the stalls in that line of code. So, and also there's another really problem here is in many cases, especially in the complex HPC programs, especially for those really large programs like LAMPS, the symptoms or the performance issues and the real root causes are in different files, and it's really hard to manually trace back to the root cause according to the symptoms. And another motivation here is actually currently there's no profiler to support the root cause analysis across architectures, because NVIDIA has NCU, AMD has Rock Profiler v3, and Intel has its own profiler v2 or unit trace. But for example, if we want to evaluate the performance probability for single kernel or for single application across architectures, I mean, one application will have different performance across architectures. So here on this figure, there are actually 11 applications running on NVIDIA, AMD GPU, and Intel GPUs. And we can see maybe 4 to 5 applications are performant on Intel GPUs, and some others are performant on AMD GPUs. Here are just some observations, but why? So why some are performant on some other architectures and some are slower? So is it because some architecture design is more suitable for this workload, or it is because maybe your code should be optimized somehow to map better the data to the hardware design? And from ICS-25 or from the work from Livermore and U Maryland, and also the some other research from Argonne from last year. Also, they are evaluating the performance portability here, but currently there are no tool to help them to go deeper to say why there is a huge performance difference between architectures. Currently, we can just apply some maybe roofline model or some other things to get some information from the hardware to know that to know something like maybe the GPU occupancy or something like that, but it doesn't help to deeply understand why the performance gap between the architectures. So based on these motivations, we want to introduce Leo. Leo is a root cause analysis analyzer across architectures via backslicing. And we are leveraging all the capabilities from HPCToolkit. And it's kind of like another layer on top of HPCToolkit. So it's very lightweight and it's very efficient. So here is what Leo can tell you, like for a kernel. Like here is one kernel from RudderPerf, which is a Rudder programming models evaluation benchmark, which contains very similar code that can run on the NVIDIA, AMD, and Intel architectures. So for this same kernel, like here are three categories. The first one is NVIDIA. Second one is first one is AMD and NVIDIA and Intel. So we can see overall here we can see from bottom up there is symptoms, and the symptoms are all can be reviewed by the vendors profiler. But all like if we want to trace upwards, there are some data flow analysis chain and the actual root cause. This kind of information can only be reviewed by our Leo here. So, and is it important? Here we can see for the same kernel here running on the different architectures, actually on the AMD machine, it is stored at the memory fence instruction, and on NVIDIA and Intel, it is stored at around some arithmetic compute instructions. So here actually the symptoms are different for the same kernel on different architectures. But actually, if we trace back to the root cause, actually they are all the same. Like they are calculating some strided memory access pattern to something like that. So Leo can tell you that, oh, for the same kernel, even though it seems like they have different performance issues on different architectures, but actually they share the same root cause, like under the hood. And how to optimize it is very easy, like just to apply some shared memory tiling or something like that, and you can. And as a result, actually, from our experiments, we can get a 2x to 3x performance boost. And our Leo is not only can be applied to this kind of kernel, it can be applied to any kind of kernels or programs running on the GPUs, and we can get really good performance benefits from that, from the insights we can get from the Leo. And we also apply these to some real applications from some kernel library, maybe hip kittens from Stanford, and we easily figure out some kernel studies underperformance, and we apply some software pipelining, and we can get some performance boost for different problem size. And also, like these kind of things can be fitted into the large language models context window combined with the source code. And by combining these kind of things, informations with the profile information and the source code things, the models can easily figure out where to pay more attention to and to apply the correct and right and suitable way to optimize the code. And as a result, we actually we can use fewer iterations to achieve better performance with large language models on many kernels. So, yeah.
Happy to take a couple of questions.
I think we have time for maybe one question while we get connected. The next speaker.
So this Leo, it's publicly available now?
It hasn't, but it will, like maybe after we submit the paper.
I think we're a couple of months away. So the thing I showed you with the donut graphs, so this is in a branch, and so we expect this to show up in a release in maybe a month or so, and then the layout piece will be a little bit behind that.
Are you looking for any other codes to optimize?
We would love to take suggestions. It'd be great to have good case studies to show off.
Okay.
Okay.